Hello, and welcome to tonight's lecture. My name is Eleni Onel, and I am the chair of mathematics department here at Stanford. This lecture is one in a series of public lectures that is organized by Stanford Mathematics Department and sponsored by the Stanford Mathematical Research Center and by the Friends of Stanford Mathematics. And in fact, if you would like to be notified about future events like this and you are not on our mailing list, then please send me an email to chair@math.stanford.edu. This evening, we are very fortunate to have as our speaker Professor David Donoho. And before we begin, I would like to say a few words about our speaker tonight. Professor David Donoho is the Ann T. and Robert M. Bass Professor of Humanities and Sciences and also Professor of Statistics here at Stanford University. He did his undergraduate studies at Princeton University, followed by a PhD at Harvard University. And he began his academic career as a faculty member at UC Berkeley before moving to Stanford since 1991. Professor Donoho is a mathematician who has made fundamental contributions to theoretical and computational statistics, as well as to signal processing and harmonic analysis. His algorithms have contributed significantly to our understanding of how to work with sparse data. Over the last 30 years, his research has focused on the overall big challenge of recovering information from symbols and images. His work includes the development of effective methods for the constructions of low-dimensional representations for high-dimensional data, developments of wavelets for denoising and compressed sensing. Among his many awards and honors, let me just mention a few. Professor David Donoho became a MacArthur Fellow in 1991. This is sometimes called the Genius Award. He's a fellow of the American Academy of Arts and Sciences. He won the COPS President's Award. Sometimes it's regarded as the Nobel Prize in Statistics in 1994, the Nobel Wiener Prize in Applied Mathematics in 2010, and also the Shaw Prize in Mathematics in 2013. So I'm really delighted to have Professor Donoho with us tonight. The title of his talk is Leaping from Blackboard to Bedside, Medical Imaging and Higher Dimensional Geometry. He will discuss the big challenge of recovering information from symbols and images and some of the mathematics behind the recent advances in compressed sensing. So please join me in welcoming Professor David Donoho.
Thanks for the nice introduction, and I want to say I have a fair amount of radiology-related imagery to show you, but I'm not a radiologist, and to the extent there's anything valuable in that, it's due to the contributions of others, some of whom I've listed here. These include Shreyas Vasanawala, who's a doctor here in the radiology department, as well as Michael Lustig, who was a PhD student here, is now a professor at UC Berkeley. There's also researchers out in industry. And then in addition, there are two other doctors that, whose significance will become clear later. The talk that I'm planning to give you here is based on a talk I gave last summer in a congressional briefing that was held at the Senate Russell Office Building in Washington, and this is the poster for that. The title was not my idea. The idea of giving a talk was not my idea. Everything is due to this man, David Eisenbud. He's been the president of the American Math Society. He's a professor of math at UC Berkeley. He's also the director of the Mathematical Sciences Research Institute. And as you can see here, he's very fond of blackboards. So he's the one who came up with the title From Blackboard to Bedside. And he also came up with the occasion and the reason for doing this. I'm a trustee of Mathematical Sciences Research Institute, and as such, I interact with David various times of the year. And in the last year or so, he's spent a lot of time thinking about the fact that at least in prospect, it seems like there could be quite serious funding cuts for mathematics in the NSF budget. So for example, at the MSRI trustees meeting that was held this last March, so just 2 months ago, we were told by a deputy director of Division of Math Sciences to expect a 10% cut. That would be something like taking out 100 investigators' awards. And so it would certainly reduce the possibility of supporting graduate students, and it would reduce the opportunities for young faculty, et cetera, et cetera. So we, obviously, as concerned about mathematics, would care about such an event. David was interested in getting in front of some Congress people with a story of how mathematics is helpful to other things that are in the national interest and are noticeably valuable to people who are ordinary citizens and taxpayers. So this is somewhat different than some of the more highbrow lectures that you will have heard in this series. It's going at a different level. As David explained to me, if you're talking in Washington, stories are the coin of the realm, and it's much better if people cry. Now, I don't think there's been much crying in the previous lectures in this series, but at least on my part, there may be some crying today. I'm likely to get choked up, as you will see shortly. So the briefing took place, and we were fortunate enough to have some top-ranked politicians show up, including Nancy Pelosi and Chuck Schumer. More about that later. And then later, I summarized essentially the argument about this in an article that appeared in the notices of the American Math Society recently, which you might want to consult. So I'm planning to go, first of all, through more or less the same territory as the congressional briefing, as a way of sort of opening up to the audience how mathematicians might try to reach out and discuss the significance of what we do, although you'll see it's quite different than any math talk you would have seen. And then after we do that, I would like to talk about how the stuff that we're talking about, which is some math that has had an influence on the technology of MRI, how it came that that technology transfer happened so rapidly. So this gentleman is here in the audience. That's my son, and this lady is my wife, and this picture was taken some time ago. You can see many things in this picture. I'm sure you can see the son's absolutely adorable nature. You can see his love for his mother and many other things. That's not the point of the picture, although I do think it's very cute. The point of the picture is this dimple right there. That marks my wife, Mickey, as a person who's had brain surgery and who benefited from that and has led a normal life afterwards. And so I think you can understand that this young man has known about her surgery practically his whole life. And so he would have known that brain surgery played a role in making his mother a whole individual and so on. Here's a second key moment, also in June. This was graduation. This is Dan graduating from medical school, and his medical school was kind enough to let my wife and myself wear our PhD gowns and to hood him in the hooding ceremony where you get the green hood of being an MD. So years of preparation to become a doctor were achieved at this moment. You can see the proud parents and the delighted young doctor. This is very recently. It was taken in this picture here was taken in the garden of Emmanuel and Candace's house with Chiara Sabati. And there's our son, and there's Mickey, and you can still see the little dimple that I mentioned in the first slide. This is our son at LA County Hospital, or else LA Children's, one of those two that he works at, and with a patient who's just, he's at some point opened up her skull, and you can see here that she has a dimple too, which is still healing. That's his patient. She's had the same type of surgery that he's known that his mother had at roughly the same age. So what has happened here is essentially the story come full circle that the child has become the man. Now, serving these patients, such as the one who's not identified here, but you can get an idea about the background that she might have from some of his comments. He serves in a large county hospital that treats a disadvantaged, economically marginal population. Magnetic resonance imaging is the preferred method for planning neurosurgery. If you're going to open up someone's head, you'd like to know what's likely to greet you. However, brain scan times are lengthy, and often you can't have that time to wait. And so often they have to open without actually getting a proper MRI, or they go and perform a CT scan by X-rays and then expose children to ionizing radiation. As he points out, it would be great to have much more MRI. It would be crucial for the services that his hospital provides. What they actually have here is a long wait time. So this is an image that our son sent, waiting in the MRI machine room for patients to become processed there. You can see the long times that an individual scan can involve. That's one patient, and there's various stages that you have to go through. That's 24 minutes, and the whole thing takes maybe 45 minutes to go through the protocol that's there. And during that time, there's a lot of medical personnel that are simply sitting idle, and the patient is immobilized and not very happy either. So we would like to have more MRI imaging in order to do neurosurgical planning, but it takes a long time to get the imaging. And so Dan's overall comment is faster, please, by which he means it would be nice to be able to do MRIs faster than we currently do. It would make a big difference for his patients. Here's another picture taken in June. This was Dan's high school graduation. So that's me, that's Dan. This is my father. And he wasn't around for Dan's graduation for medical school. So in between high school graduation and the 11 years later of medical school, he passed away. What was going on during the time of this particular picture was a cancer of the prostate was growing inside his body, and it was undetected until it was really too late to do very much except manage the whole process from then on. So after my father's death, I learned a bit about prostate cancer diagnosis from Dr. Faye Stern, who has been spearheading an effort to improve prostate cancer diagnosis. It's the most common human cancer. The typical way to identify it is by biopsy, which is simply a shot in the dark. It's possible to repeatedly miss prostate cancer, biopsy after biopsy. But if you used MRI, you could actually increase your chances of detecting it by a factor of 5. A study at Brigham and Women's done together with Admitech has shown this. The result would be better detection, and that would drastically reduce the cost of this disease to society. As an example, Dr. Stern cites this case study of a 53-year-old African-American man who had increasing PSA, but a long series of biopsies, year in, year out, leading to 10 negative biopsies, failed to find anything repeatedly. Finally, MRI showed that there was aggressive cancer with metastases, and the treatment following that cost more than $600,000 over 6 months. The MRI only cost $1,000. Early treatment would have been much less expensive. By having all these blind biopsies, we just accumulated a tremendous debt load. So we've got the most common human cancer, often not properly diagnosed and leading to very significant costs to society, and MRI is an example of a way to reduce those costs and improve patient health. So we would like to have more MRI, and I can tell you that help is on the way. So last year in the spring, so 1 year ago, a series of commercial devices that dramatically sped up the acquisition of MRI data got FDA approval. And these are now available on the marketplace and are becoming commercially available. So I'd like to talk a little bit about that development and then finally lead into the role that mathematical research played in enabling this fundamental speed up in this important task. One of the products is produced by GE, which is a large manufacturer of medical imaging and has a very tight relationship with research being done on this campus and licensing agreements and so on. So the product, as they call it, is HyperSense. This is an article by a professor at Cambridge University Hospital describing the benefits of using this product. And essentially, what's being shown here is the bioequivalence that you get the same imagery, only much, much faster by using the new technology. So the imagery has been judged to be bioequivalent. It's just as informative, just as diagnostic, but it's gathered at a speed up of 8x in this particular case.
What is B?
So I believe that A is the traditional and B is the proposed, or the new approach. Siemens has a device of its own which is more specialized. So I should say this is multi-site, so it can be used all over the body. The Siemens product initially was designed for imaging essentially the beating heart very efficiently. And this is some of their marketing collateral that you can get at the Siemens Medical Imaging website, Siemens Health and Ears. The benefits that they list are that you can take the imagery while you're free breathing, so you don't have to hold your breath, and you get high resolution imaging. And there's no gating or some specific synchronization with part of the cycle. Many more patients can put up with these requirements than what happened previously. Instead of a 6-minute imaging based on multiple breath holds, you can do everything in 25 seconds with free breathing. There's an example here provided to me by Siemens, for which I wanted to thank Edgar Mueller. And you can see here there's the two different ways of gathering the data. One of them took 25 seconds, one took 6 minutes, and these are bioequivalent. You can extract the same information with the same confidence from these. Pardon me. these particular products, which are on the market, are simply the tip of the iceberg. And we have here some particular researchers at the two major providers who have gone all in on this, pointing out that they see that compressed sensing is something that they'll be able to use all through all the MRI products that they offer, or all through all the MRI applications that they're aware of. So compressed sensing is the term of art that first arose in the mathematical sciences literature for this approach, and you'll notice that it's actually being used by the vendors, so that not only is there an influence, but they acknowledge the influence. In pointing to this as being just the beginning of a transformation, I'll just mention briefly some things that are not yet to market, but that are quite interesting. So here are some slides provided to me by Shreyas Vasanawala, a doctor here in radiology at Lucille Packard Children's Hospital. He's been working on improving MRI from the point of view of benefiting pediatric patients. Children are fidgety and very anxious. It's difficult to get them to sit still for periods of time like an hour or 45 minutes. It's important to get the data very quickly. The alternative is to sedate them, or if you don't want to sedate them, to X-ray them, and then that produces radiation dosage, which might be ultimately bad for their offspring and so on. In 2009, they did landmark work, Vasanawala, together with Michael Lustig and others, speeding up pediatric multi-site by 6.5 times. And as you can see, that was work done at Packard. And then that's propagated so that vendors are today offering commercial products. What he's working on these days is cardiac cine, so it's somewhat similar to the Siemens product. What you see here is an image where you're taking data. I'll just read out his letters. Hi, Dave. It's a movie that shows a time-varying vector field of flow, the velocity of blood at every point in space and every point in the heart beating cycle has been captured in under 10 minutes. It's captured in such a short time as only possible with compressed sensing. Since we can capture the entirety of the anatomy and physiology in a comprehensive way, it replaces our conventional iterative serial data acquisition that takes over an hour. For instance, first find one part of the anatomy, use that to find the next, etc. The big impact of this is that children can get scanned without anesthesia. Those that still need anesthesia can have a shorter, lighter sedation. Because these children have heart disease, it's a big advantage to reduce the risk of anesthesia. So instead of an hour, we just need them to be fairly calm for less than 10 minutes. And it's possible not just to produce images, but to produce movies, and not just of ordinary imagery, but even of vector fields of flow. As it turns out, this is now used routinely at LPCH, and multiple times a day. The benefits are the less anesthesia, or if there is anesthesia, you can make it lighter. Here's an example of imagery taken very rapidly, and the child is breathing and fidgety and whatever, but in just the seconds that they were able to acquire, they got sharp imagery of the kidneys despite the lack of immobilization of the patient. And so that's soft tissue that you wouldn't be able to learn from X-rays. Siemens also has a number of cutting-edge applications that are not yet to market. Here's an example where they're doing traditional slow cine MRI of the heart, gathering data over 9 heartbeats. You see blurriness because if you have to go over multiple heartbeats and combine, there's the possibility of blurring. On the other hand, you can get diagnostic images in one single heartbeat and create imagery that's quite sharp using the newer techniques of compressed sensing. In fact, you can even get 3D cardiac CNA MRI in less than half a minute. This is quite different than what anyone would have thought 10 years ago. It's not yet a product, but these things are being done in routine research environments. So I've mentioned that we're seeing big advances in the speed of MRI scanners that are coming to market and near market. I did want to point out that mathematics has been important for its advance. So I do also want to point out to you, if you happen to be congressmen, this might be important, that math research is federally funded. And so I'll mention, because they'll figure into the story later, Professor Condez and Professor Tao, who are two well-known mathematicians funded by federal funding, and they were funded federally at the time they did the work that did contribute to the advances that we've seen. How is it that mathematicians could have an impact on this? Oh, and by the way, I have them at the Blackboard here to make the point that there were Blackboards, so David Eisenbud could be happy about his title. Okay, well, how could math help this? So I'm going to talk to you about something that you can agree seems like math, and then later in the talk we'll understand what the connection is. Here's an object I'm going to call a cone, and I'm going to call this a plane. And I want you to think of that plane as being swiveling around the apex of the cone right there in such a way that it can have lots of different positions. So there's a whole space of positions that it could have. And in some of those positions, it might slice into the cone, and in some other positions, it might miss the cone. So just to make that point clear, we have an animation showing some of the different positions that you might have. Here it's missing, here it's slicing. So you can see there's a lot of positions that offer either of those two possibilities. So as it turns out, and mathematicians are people who show that one thing is equivalent to another despite the fact that you may not believe it to begin with. And then they take you through it and they make you believe it and make you understand it. So a mathematical fact is that the following are equivalent. We can ask exactly the question that I was showing you before, except we're going to do it in very high dimensions. And that's going to be exactly equivalent to saying that we can speed up MRI in some model of what the MRI system and imaging does. So there's a particular statement here, and don't worry, it's going to come back again and again in the talk, and we'll decompose it and make it clearer and clearer to everybody. But if we're in a million-dimensional space, and we consider a particular kind of simplicial cone that has an apex that instead of being a point is actually a ridge, like a linear subspace of dimension 10,000, then we ask the following question: if this is a 900,000 dimensional plane, is that going to slice the cone? So it's the same question, we just changed all the dimensions. But it's really the thing that you just saw. And we'll explain as the talk goes on how that's the same thing as saying if I have an image that's 1,000 by 1,000, like it might be produced by a digital camera, with a certain number of so-called non-zeros, then we only need a certain number of measurements, and that's much less than the number of pixels. So these are equivalent facts. And mathematicians show you how to go from one of those to another. Then you might ask yourself, well, what good is that if you don't know the answer to either one of them? But mathematicians do know the answer to the first one. And we can take a simpler version where instead of a plane, we just had a line. And then you'll understand that mathematicians know this. They can do this. Okay, so here's the same cone, and we just have a line going through its space of positions. And you saw that in some cases, it slices in, and there's some other positions where it doesn't slice into the cone, right? And you can recognize that what's really going on is that when the line emerges from the cone you can imagine that there's a sphere and that the cone is something whose boundary is just inscribed on the sphere in this way. And that just like we had that point moving around, there's where the line emerges from the sphere is a point, and the point can be at various places on the sphere. And there's sometimes when the point's inside and sometimes when it's outside. And the fraction of time that you get the line inside the cone is exactly how much area is inside the cone. Now, there's a famous theorem by Gauss, which is that actually when you have a triangle on the sphere, the sum of the angles is not 180, but something else. And actually the area of the triangle gives the deficit between the sum of the angles and 180. So for hundreds of years, mathematicians have been figuring out these kinds of things, and they know how to calculate them. And you even have witnessed one of the simplest examples, because it must have occurred to you that if you have a very big triangle, the angles don't sum to 180. At least it was shown to me when I was in grade school, and it's an easy thing to check for yourself. So this has been part of math for a long time. We've got this. Of course, we're working with a very abstract way of thinking about problems, and it doesn't seem that knowing the answer to a problem like this could be useful. But that's exactly what makes it useful. The fact that mathematicians can solve problems at this level of abstraction and generality means they have applications all over the place once you understand how to set up the connection. Now, the transfer of ideas like this slicing problem into something that could benefit patients depends on there being a whole chain of transmission of information and work being done by lots of people. One of the most important persons in the particular chain that we're talking about here is Michael Lustig, who was a PhD student here. And this, of course, is the Stanford campus that we're looking at. I showed a schematic map of campus in the briefing, and the point here is it was very important in the transfer of the technology that a great university has been established in which you have excellent departments in the mathematical sciences and in engineering and in medicine, and they're all in walking distance. So basically, this is the EE department is here. My office is here. Mickey Lustig used to come and look in my window and knock on it and so on, and then we would have conversations. And he would go to the math library, which is in this building, and then he would read some stuff. And there was a trailer parked back here that had an MRI scanner in it that had been donated by GE. And he would do some experiments. And then Stanford Hospital is over here, and he would walk and talk to Vasanawala about things that he was finding, and then end up back here with John Pauly developing some new pulse sequences that would allow rapid acquisition of data. So he was really like a kid in a candy store for his PhD. He benefited from having all these facilities together. And in fact, in all of these things, you really have genuinely world-class facilities there, so that he really was able to do cutting-edge work, benefiting from the best advice available on Earth in everything that he was doing. Another example of how the research funding systems work is I point out that Professor Condez and Professor Tao had done some important work in this area. So I just wanted you to know that some of that work took place at IPAM, which is a NSF-funded math institute that's right here. And this is on the UCLA campus, and that's the math building at UCLA campus where Terry Tao had his office. And they were just walking across the street and talking to each other. And I and a number of other people were brought to the UCLA campus in the fall of 2004, at which a lot of work on this went ahead, and it became clear that the math was all right for doing what we're talking about. So this, again, is a special set of circumstances that was created by federal funding. So we're seeing that industry is delivering and academia has delivered, and the FDA has found these things to be bioequivalent, and so you can speed up without any loss of data quality, et cetera. So that's pretty much the end of the briefing, and then after that, the American Math Society published on their blog some information, and you can see that they really felt they have to, bang the drum and explain the significance of this. So let's see, can I walk over here? So they point out that there's 40 million MRI scans a year, 80 million globally. These sorts of speed ups are quite important. There's about 30 billion a year in MRI direct bill to Medicare. And so speeding up this equipment is actually very beneficial to the federal budget in the long run. The math research budget of NSF is $250 million, so it's not even 1% of the annual billing. So a significant reduction in MRI costs or increase in functionality is being achieved really with a tiny, tiny amount of money, relatively speaking. And then to cut that tiny amount of money back by 10%, well, you just don't know exactly what you're losing, but why would you do that? Okay. Now, there's another why, which I want to bring up, which is, why did this transfer happen so quickly? I mean, the mathematicians are used to the idea that they do stuff and no one notices for 100 years. And then it still seems strange that mathematics would be helpful, in something that's dominated by questions of patients and hospital facilities and so on and so forth. So I wanted to make some comments about that. But before I go on, let me just check my time. Okay, so let me put a few things in perspective. Professor Condez and I have both spoken at the big meeting ISMRM, and there are thousands of active researchers. I think the biggest audience that I've ever had in a talk was at ISMRM in 2012 in Melbourne. I think I had 5,000, probably 2,000 doctors, 2,000 physicists, and so on in a talk that I gave. There are many people out there to do the work. They've all wanted to speed up MRIs since forever. Nobody wants it to be slow. There actually were people researching and proposing that you could speed up MRI for decades, as you're going to see. But no one really understood what was being achieved in the experiments that were being presented. And the fear, uncertainty, and doubt factor was crucial in limiting, let's say, getting grant money to go after those experiments and following up on it. What math gave was principles, certainty about what you're talking about, and also very valuable heuristics to communicate to people. So it did persuade and inspire many people. So there's all the people there to persuade and be inspired. As it happened, within a few years after the original compressed sensing papers, the #1 topic at ISMRM meetings was compressed sensing, and the most number of papers, the most number of talks, so on and so forth, in quite a large meeting was on this one subject. So let me explain something about how the result that I showed you before led to a communications advance that helped break the logjam that was keeping people from exploring this. So I'm going to color the different parts of this equivalence in the following way. So you see what corresponds. So this corresponds to that, this corresponds to that, et cetera, et cetera. So there are particular elements here that are mapped into each other under some correspondence. So there's a certain number of non-zero wavelet coefficients that are being hypothesized. The image has 1,000,000 pixels, just like the space has 1,000,000 dimensions. There are 900,000 dimensional plane. By contrast, there's 100,000 random measurements. So there's a certain way that this correspondence happens. And the key thing as you look at these results, you see that there's certain things that are being assumed that have to all be just right to make this work. Once you understand what has to be there in order to make this work, you can develop a way of talking about it that can be communicated to other scientists, and they can develop a way to think about how to make all those things come together. So Michael Lustig, when he was a grad student, I remember we had conversations about this, and one of the great things that he did, among many, was develop a communications strategy for explaining this to scientists in his area. And so I'll call them here the basic heuristics. The idea was, tell the scientists there's 3 things they need, and this mimics some of the assumptions that are in the basic theorems. And then explain to them what those are, so they'll not have the mistaken conclusion that you only need 1 of these or you only need 2. Because really 3 things have got to come together for this special situation to manifest. So these were packaged by Lustig as 3 particular slogans, and it seems that this took in his community. So first of all, you have to be dealing with imagery that is in some sense compressible, that if you ran a standard data compression tool on it, like JPEG 2000, it would compress nicely. You've then, when you don't take all the traditional data but undersample, but you have to do it in a way that's kind of random. And then finally, you can't use all your old linear algebra for recovering, but you have to do something nonlinear. And then in order to keep these things in people's minds, he chose very particular graphic emblems, and in his talks would teach them about these particular ingredients by explaining what the emblems meant. So I'll briefly say something about each one of these just so that you also know what these are referring to. So let's first talk about what the first emblem means. In the 1980s, some applied mathematicians developed tools called wavelets, which could be used, for example, for doing transforming one data set into another form that was maybe more convenient. The wavelets have a multi-scale nature, and they turned out to be useful for compression. If you take an image of this castle and look at its wavelet transform, you see that you get something that has a number of significant coefficients, but also a lot of very insignificant ones. That you've transformed something preserving the total number of coefficients. It would still, if it's a 1,000 by 1,000 image, it would still be 1,000,000, but many of the resulting coefficients are effectively 0 after wavelet transformation. And So once it was understood that wavelets did this, they had success in being adopted in various standards for data compression and transmission. And we mentioned some of the applied mathematicians who were involved in this and whose work contributed to it. A second increase, so it's important to have compressible signals so that a wavelet or similar transform can go to work on it and map a lot of the coefficients into zeros. It's important to undersample in a kind of a random way. And what was traditional in MRI before would be to take K space or Fourier space and sample everything, namely every pixel. Instead, the suggestion was to sample pieces of it, either randomly selected pieces or pieces that were designed to be somehow strategically chosen. And then finally, the reconstruction has to be done by a method that's not the traditional linear algebra. And to explain that, the emblem that was used is don't minimize the L2 norm of coefficients as people were used to doing in so-called ridge regression or method of regularization. Minimize the L1 norm as people were using in methods like basis pursuit, lasso, and so on. The difference is that the different shape of this ball meant that there was a different relationship of the minimum norm point within the data plane, the plane of possible underlying objects consistent with your undersampled measurements. So if the data truly were sparse, which would place them near a low-dimensional hypercross, then the structure of the L1 norm made it at least plausible that you would select it out correctly. But that would never happen if you were minimizing the L2 norm, even though the L2 norm is traditionally what everyone had always been taught to use ever since Gauss. So there's your three emblems of what has to be there. Then you can go out, explain this to scientists. They can understand that there's no free lunch. You need all three things, and they can think about it and figure out how to get that in their application. Once the basic heuristics were understood, it was possible to go back in the literature of signal and image processing over decades and see that many, many times people came close, where they would come up with one or two of the ingredients that were necessary, and they would propose that those one or two would do the job, sometimes three. A very close example of this is in the paper by Jeff Hoke, a good friend of mine, and his co-authors in the mid-90s, pointing out that you can improve NMR spectroscopy by recording for less time, using random sampling points, and using a certain kind of convex optimization somewhat related to the L1 that we just spoke about. It wasn't specifically said in this paper that you also needed sparsification, but when you look at the examples in that paper, you see that where they used random sampling and got good results, the object being recovered had only a few bright spots and everything else dark. So sparsity was playing a role in that particular result, although the articulation that you needed all three items, namely random sampling, sparsity, and convex nonlinear optimization, that realization was not as it was partially implicit. Closer to the present day, so a few years before the compressed sensing papers hit, it was already known in MRI that there were good results you could get combining random sampling and a non-convex minimization approach based on a kind of a Bayesian argument. And the claim was made that you got scan time reduction, for example, in Frank Wyer's thesis. However, again, this work didn't have the impact that it might have because it was experimental and it wasn't well understood why one should rely on it. So we have a question why computing experiments were not persuasive, even though there had been many, many of them. The thing is that as modern scientific methodology research has become computational, a lot of it is ambitious and pushing the edge, and that means that other people can't really get those same results. They don't have the code, they don't have the data, they don't know all the details. And it's also a habit people have to not share their data and code, and that's unfortunate despite regulations that say you must, they don't. And then it became endemic in many fields that people just don't believe other researchers' computational results. The consequence of that is that progress is not cumulative, and so you can look back in the literature and find glimmers here and there of computational experiments that suggested something might have been true, but they were apparently not followed up on with the same vigor that has happened in this particular case where we had mathematical confirmation. So it seems that, at least under the old rules that we were living by with the computational hygiene of the past, we could endlessly reinvent similar procedures and endlessly claim that there were improvements without actually cumulatively changing practice anywhere. John Claerbout, who's earth scientist at Stanford, long ago pointed to the problem that research relying on computation was getting into. That basically the problem is that all that computational research is only just making an advertisement saying that you had an experience and it was great, and you move on and nobody else can have that same experience. So the computational era that we've entered lacks something for releasing the energy of true innovation. On the other hand, math, at least in this instance, was persuasive because it's so clear and, as you'll see in a moment, precise in what it's claiming to offer. Of course, rigorous, and it offered this heuristic content that I've explained. So let me just quickly point out the little set of equivalences that turned out to be convincing. So you've seen before this particular phrase, and the key thing that mathematicians found is that they could figure out this probability of a random plane slicing into an appropriate cone in terms of they would just need a couple parameters about the problem. So basically the dimension of the apex of the cone, the dimension of the space that's ambient, and the codimension of the plane. And then if you just calculated two variables, you could tell whether you were going to have slicing or not. And generically, you would either have no slicing or slicing, depending on where the variables put you in this phase diagram. So it became very simple to understand when something could work, and it really only depended on things that people could do on the back of a napkin and understand. And of course, it's just the truth. So that's also an advantage over interpretation. So once you understand this problem really well, and then you go on to translate it, where you take the math and see what it means in applications by translating from each piece of math into the applications, you see what we're talking about. The reason that the cone and the hyperplane and so on are coming in the connection with mathematical imaging is because somewhere we're using this L1 minimization, and there's a question about the contact between the L1 ball and a certain hyperplane. Will that contact be clean, transversal, or will it be messy? That's exactly the problem that's been solved here. If it's clean, it's going to turn out that you get good reconstruction despite a lot of indeterminacy in the problem. And so the question of when this methodology that we introduced earlier is actually going to exactly reconstruct translates over into this geometric question, and then there's an answer on this phase diagram. So the summary is that math has indeed gone from Blackboard to Bedside. There are benefits to patients, taxpayers who are paying for tens of millions of these scans, and you can get more patients handled per unit time, and to physicians like my son Dan, who have to do surgical planning, and they'd much rather avoid unpleasant surprises when they open the head. Finally, math has helped here because it has such clarity. It has its own way of persuading and inspiring, and it has an advantage over sort of data science and computations exactly in that nature. And it can unleash a lot of work by other people because there's so much confidence in the accuracy of its conclusions. I want to say that we should add a few other things. One is, a big part in the transition story is that Stanford has a great EE department, and inside there is an MRI lab, which has historically been very influential in MRI, and there are long-term relationships between Stanford, GE, and Siemens. So the fact that this work came out of Stanford certainly had a great deal of impact on industry. John Pauly was Michael Lustig's advisor and co-author on these papers, and certainly needs to be mentioned, of course, and I didn't want to miss that. I also wanted to mention that there's a patent on this, which is held by Stanford University, and part of the reason that the vendors are willing to credit compressed sensing is because Stanford has pretty liberal licensing terms with Siemens and GE. They get these patents for not very much money, relatively speaking, because they license pretty much everything that Stanford does in this area. And so as a result, they're going to say honestly, yes, we're using this. Whereas if there were a more difficult relationship, they might not acknowledge the contribution that's been made in this case. Finally, I want to point out that the transition from math to industry had a lot to do with the specialness of some of the individuals involved. So Michael Lustig and Shreyas Vasanawala, who I've mentioned several times, this is not the only thing that they've worked on or done. So you can find this, and I want to thank Davey Hubei, the graphic designer for this presentation, for bringing this to my attention. They have another project going on where they're not revolutionizing algorithms or scanning sequences. They're trying to revolutionize the hardware associated with the receiver coils by creating a flexible skin, so to speak, that you can put on the body and use that in order to be part of the MRI data gathering device. By having flexible coils, they believe they can also they can also further accelerate in a complementary and additive way above whatever you could do by compressed sensing. They are working at a company now called NK-Space, together with Professor Ana Arias, who develops flexible electronic circuits at UC Berkeley in the EE department. So another reason that we had rapid transition, in addition to patent facilitation, Stanford's reputation, and so on, is really Michael Lustig and Shreyas Vasanawala are quite special people who are driving innovation wherever they can. Thank you so much for your attention.
Vaughan Pratt, Stanford University. A question about that curve you drew. Does that mean that you should be pushing the codimension of the plane ahead of the dimension of the cone?
Well, definitely it's telling you what's the good range for the variables involved. Now, where you can push things depends a lot on understanding how the math translates into practice. So pushing tends, so as an example, it might tell, once you understand that diagram, it might tell you that 3D MRI is fundamentally a better place to be doing all of this than 2D MRI. And the reason is that the sparsity is going to be better for imagery in high dimensions than in low dimensions. So there's various implications of the diagram, and you're right, we should pay close attention to it. And it leads to heuristics of what applications are the best. That's certainly all embedded in that diagram.
Thank you for a very interesting presentation. I was wondering, Congress has its own logic, it's not always rational. So I was wondering, what was the outcome of your presentation? Was the funding preserved?
Yeah, so as late as this last March, we were expecting a 10% cut. That's what NSF was telling everybody. In the end, it's like a 1% increase, or anyway, a small percent increase. So we've staved off the wolf at the door for, at least until next year, I guess.
Thank you. I just had a question about the narrative. You've outlined how a set of very smart people and how they recognized how this the methodology had to be presented to the community or to across several communities in order for people to be able to move forward different disciplines. But I'm not sure I understand how you can generalize that. There were a lot of special things about this. For example, Lustig himself, he was kind of a special person. He recognized that there were 3 components, for example, that had to be emphasized to the communities. And I just wonder if you could expand a little further, or whether it's possible to sort of codify the the methodology to make these advances, these collaborations between mathematics, physics, engineering, and medicine, in this case, so that this can be replicated in other problems, and perhaps more generally, maybe it doesn't necessarily involve these particular disciplines, but is there a generality to these lessons and the heuristics and things that you talked about that could be distilled and made available? And secondly, second question, unrelated, is 2D versus 3D MRIs. I'm just curious. I don't really know too much about it, but I guess I thought that you're getting a volumetric reconstruction no matter what you do, and then it depends on how you slice it and dice it later. But I guess that's not really the case. It's a very different mathematical technique. Anyway, there's sort of 2 questions there. The first one's the more simple. Okay,
so the second one I'll do first because the answer is shorter. So an MR physicist designs a pulse sequence which generates magnetic fields that turn the body into a radio frequency emitter, etc. And it's possible to design pulse sequences specially to do 2D MRI. It isolates one particular slice of the body, and then only that slice is going to be generating data. So it's just in MR physics. It's just part of what the physicists do. Okay, your first question is what is there in all of this that generalizes? So the first thing I want to point out is it's very important to talk to people and to interact and to kind of try to really learn what the other people are about, what they care about, and what is really important in the way the other people are thinking about things. If you come at things too arrogantly, then I think you'll have a stillborn collaboration. A, people won't tolerate your personality, and B, there won't be the opportunity to share just that right observation at just the right time that makes everything click. So it's important to have a commitment to actually interacting with people, and so definitely Michael Lustig is very interactive, and the story that I told you about the NK space result. Sorry if I could go back here. I guess I don't have it anymore on the screen. Is that he definitely went up to somebody who was in electrical engineering, producing circuits on flexible things, and said, "Oh, great, teach me what I need to know to tell you how to do the right stuff. This is going to be something that could really make an impact in MRI." So he definitely had that feeling of fearless interaction, and that's stood him in excellent stead through his whole career. So he's now clearly a serial entrepreneur in that sense. But other people can do it. It's very important to buddy up with people and exchange information with counterparts. So now how does that generalize? I think there are, funding agencies and grant programs and so on that try to encourage these kinds of collaborations. And you see different math institutes offering things like research in pairs. That's a program at Oberwolfach. And there's some other similar programs, maybe one at MSRI, that allow, a few people to congregate in some place and work on something intensely for a while. That's needed for some of the things we're talking about. Either that, or you have just the best people in the world all on the same campus. So, we're very fortunate at Stanford in that way. And that's part of the story here, is sort of a natural environment for people getting together with really good collaborators.
Thanks so much, David. That reminded me actually some sentimental recollections of reading John Claerbout in mid-70s and late 70s when I was working on applying B-splines in geophysics, actually just about this same thing. But I was wondering why you didn't mention anything about machine learning's potential to speed up the diagnostic itself. Is it because of your focus on this compressed sensing, or you have a position that is behind this?
So, Andre, it's an excellent question that you're asking. Everywhere you turn these days, you learn that AI is eating the world, and that there's going to be nothing left for anybody to do except maybe to make sure that the computers stay plugged in, and or to watch the other people to make sure that they're watching to see that the computers stay plugged in. I'm not sure what other jobs will be left. The interesting thing about deep learning is that it would, based on what I've said in this talk, empirical results are not really trustable. Computational results are kind of flaky and dodgy. And because of that, there's a lot of noise out there where people are claiming things and other people are doubting and so on and so forth. So I'm not sure that there's been a fundamental revolution in understanding what deep learning is doing. I know that it's in a better place because of the use of the common task framework, where everybody in a certain field is only trying to solve one narrowly defined problem with a defined metric using a defined data set, so you can adjudicate whether something is an improvement. But that seems very, very narrow. It seems not so clear that if you make a big advance in such a narrow problem, that it's going to generalize well to novel situations. So it's possible to maintain some distance from the deep learning enthusiasm. At the same time, it's very important to understand that, yeah, the claims are out there that this time is different, and all these computational results are going to sweep away all need for any math. It's out there. Yeah, people believe it. So I gave a talk in Beijing a month ago, and I spoke about various things that had nothing to do with deep learning and anything in my talk. And then a young woman stood up. I gather, she might have been a senior in university years, and she says, "Since we have all these results from deep learning which are so awesome, why do we need statistics?" I mean, I had to say something. So I think that's a more pointed version of the same thing that you're saying. So I told her that, deep learning is like a horse that just won a race, and it's this season's winner of the Kentucky Derby or whatever. And statistics and the mathematical sciences more generally is like the racetrack. It's like the breeders and the doctors and the whole system of evaluating methods that could be used and understanding them and improving them. And so you're basically saying that because one horse just won one race, you don't need the doctors, you don't need the breeders, you don't need trainers, you don't need sires and dams, you don't need any of that. You've got this one horse.
So it seems that the MRI data was being represented in a very high level and abstract manner. So my question is, would you say that there is something particular to MRI that makes it especially applicable, especially suitable for applying the mathematical concepts you talked about?
Oh, excellent question. Thank you. So MRI is very suitable for this particular theory for the reason the theory is asking you ideally to essentially take a random projection from high dimensional space down to a lower dimensional space. And random means something kind of technical for the theory. So in some other applications, it might not be very easy to just decide what measurements you want to make. But you have these thousands of MR physicists who are very proud of their ability to generate pulse sequences that will generate extremely sophisticated magnetic fields and do all sorts of wonderful things in measurement. So they almost take it as something they were born to do, was to make measurements of such sophisticated nature. They take it as a challenge, they enjoy it, etc. In some other field, you might not have all the prerequisites to make the right kind of measurements for the theory to apply.